So the last of the different variables that control environmental change that we'll look at is what's summarized here as continental drift, but is more accurately referred to nowadays as plate tectonics. So the relationship between plate tectonics and environmental change can be explored in several different ways. Spatially, there's the idea of how at any particular given time that the plates are distributed over the surface of the Earth. We've also got to bear in mind the impact of crustal recycling, whereby we will subduct and destroy parts of the crust, and the pronounced environmental consequences of things such as the volcanic episodes and the volcanic activity that can accompany that. And we've also got to think of the significance of episodes of orogenesis or mountain building, principally because of the way in which mountain belts and mountain chains can interrupt the flow of air streams through the atmosphere. There's another dimension as well, which of course is that the geological investigation of environmental change brings, and that is of course the idea of how events and processes change over time. So for example, changing distribution of the plates over the surface of the Earth over geological time is going to be one of the key variables that we'll look at. Just to remind us then on the concept of geological time, what you have on the left hand side here is firstly a principal twofold division between the Phanerozoic and older rocks, and then a threefold division of the Phanerozoic into the key principal eras, the Paleozoic, the Mesozoic and the Cenozoic. So this threefold division. Now within that then I've labelled up the key geological periods. In some classifications, the Mississippian and Pennsylvanian, shown here as separate, are united under the Carboniferous, and I've put in the key ages that I want you to bear in mind for this part of the course. The Cambrian at 541, the end of the Paleozoic at 252, the end of the Mesozoic at 66, and then because we will be looking at the Cenozoic, the third and most recent interval of the Phanerozoic in more detail, I've provided details of the key ages that I want you to be aware of for that, and these are those of the boundaries between the various epochs of the periods of the Cenozoic. So for example, the Paleogene to Neogene boundary between two periods is at 29 million years. The boundary of the Paleocene to the Eocene is at 56 million years, the Paleocene and Eocene being two epochs within the Paleogene period. The final aspect that I want us to look at is how the issue of plate tectonics involves environmental change, not only in the sense of the solid Earth, but also how it impacts on the atmosphere and on the oceans. So in other words, it's not just a geological, but also an oceanographic or an atmospheric issue that we have to think about. So here's a map of the modern day distribution of the key plates over the surface of the Earth. You can see, and we'll come back to this in case it's not familiar, you can see that the boundaries between these picked out in the black lines are indicated by a pair of arrows, which in some cases are in opposing directions, as in here pulling apart, but here coming together. And these show the relative motion of the two adjacent plates. So here these two are pulling apart, here these two are being compressed against each other. The third variant of that is shown here, where one plate is quite literally slipping past the other. Now principally those three arrangements then create three key boundaries. The last I referred to, where the two are slipping past each other, is a transform boundary. Where they are pulling apart, a divergent boundary, and where two plates are coming together is a convergent boundary. And you can see in this schematic here the distribution of them over the idealized surface of the Earth. And you can see the other features that are associated with them. For example, subduction here, the creation of volcanoes. You can see here creation of a major mountain range, including ice caps on the top of some of the mountains, thus a change in the albedo. Volcanism here associated again with subduction. I want you to notice here how this molten hot rock is actually being brought up to the surface at these spreading ridges, thus changing the temperature gradients with depth as you go below the ocean floor. We'll come back to all these points that are encapsulated in this image shortly. I need to make you aware that there are two alternatives as how do we actually describe the upper part of the surface of the Earth. If we are using a chemical classification, if we're basing it on the composition of the rocks, then we can make a threefold distinction between the mantle, which is iron and magnesium rich lithologies. One of the key lithologies in the upper part of the mantle is peridotite. And then we have above that a granitic continental crust making up the continental cores, and then the ocean crust shown here. You'll notice that the density of these two is different. The higher density oceanic crust is predominantly basalt and around 7 kilometers or so thick, so a very fine-grained basic igneous rock. The continental crust, on the other hand, is less dense because it's preferentially enriched in elements such as aluminium and silicon. So that's if we're doing it on the basis of a chemistry of the upper part of the Earth. If, on the other hand, we're actually looking at the mechanical properties of the upper part of the Earth's surface, what we want to do here is divide it into two broad divisions: lithosphere, and you can see the term applies to both continental lithosphere and oceanic lithosphere. The key issue with that is that it's rigid, which sits then on the asthenosphere, which is solid but extremely viscous. So effectively it's plastic. So the lithospheres then, the distinction between it in terms of continental and oceanic refers to which the upper part of this twofold division that you see here is. In each case, it's a lower layer of peridotite in the upper part of the mantle, which is rigid, and it's either capped by then the basaltic ocean crust or the silica and aluminium rich continental crust here. And these, in a mechanical sense, are rigid. They behave as one, and that's what we understand by the concept or by the term tectonic plate. It's effectively synonymous with lithospheric plate. Now these essentially rest on the asthenosphere. Temperature, of course, below the surface increases with depth. You can see here the 1300 degrees centigrade isotherm. An isotherm is a line of equal temperature. But the rocks, even at depth, remain solid, though plastic, because of the effects of pressure. They don't melt. These rocks, in terms of their mechanical properties, are considerably weaker than what lies both above them and below them. One key point I want you to be aware of is that then this asthenosphere, these rocks at elevated temperatures, reach right up to the surface of the Earth at mid-ocean ridges where new oceanic crust is being formed. And that is very, very important, as we'll come back to later, in terms of controlling the volume of water that can be held within the ocean basins. I'll briefly discuss how these tectonic or lithospheric plates move. In short, it's much debated. The detailed understanding of it is not complete. There are two principal mechanisms, the older of which is now less favoured, but envisaged large-scale convection cells in the mantle that would circulate, creating zones of upwelling at the mid-ocean ridge and then facilitating the sinking of older, colder crust further away laterally. And then the second mechanism, slab pull. The slab pull model, on the other hand, envisages that the newly formed oceanic lithosphere that's being created at the mid-ocean ridges is hot and buoyant. It's less dense than the asthenosphere, and as the buoyant magma pushes up, the plates are driven apart either side of the mid-ocean ridge. Subsequently, that oceanic lithosphere will become denser with age as it cools, and it'll thicken by addition of new material on the lower surface of it. And eventually, in subduction zones, that oceanic lithosphere will be subducted and recycled deep within the earth. And the key element is that this slab pull element, where the old dense heavy plate sinks, drags the younger cooling oceanic lithosphere laterally and ultimately down into the subduction zone. So let's just briefly look at some examples of the three different types of plate tectonic boundary. The classic example of a transform boundary where two plates are moving past each other. So here's the North American plate moving in a relative sense southwards compared to the Pacific plate, and that's happening across the San Andreas Fault. Here, of course, is an image of the mid-Atlantic ridge, a classic example of a divergent plate tectonic boundary where new oceanic crust is being created. And just to reinforce the point that I mentioned earlier, look at the trajectory of the 1300 centigrade isotherm, the line of equal temperature here. It's effectively at the surface at the mid-ocean ridges. And of course, what that hot, buoyant material is doing is then going to be relatively elevated compared to the older crust, and that's going to control then the volume of water that can be held in the ocean basins. If the level of activity at the mid-ocean ridges is reduced, then there's less hot, buoyant magma injected into the system. On the other hand, if the mid-ocean ridge activity is particularly elevated in the world's oceans, their volume can only decrease as a result of that. And if their volume decreases, the water that's held within them has to find somewhere new to go, so effectively it's going to migrate via transgressions onto the margins of the continental land masses. Convergent boundaries are of various different types. An oceanic continental convergence is where the oceanic lithosphere then is subducted under the continental lithosphere. You can see this is a Andean type subduction after the Andes Mountains in South America, and that's one of the examples we're going to look at later on. The continental plate overall is held at a higher elevation because of its lower density, so the denser oceanic plate is subducted under it, and the key then is the formation of a mountain range with all the effects that that's going to have in terms of altering atmospheric circulation with increased sedimentation rates both into the oceans offshore and in this case to the right as we look onto the continental landmass. The volcanic activity, of course, could potentially be significant with outgassing from the volcanoes, etc. So you've got these three and many other, but these three principal variables that we've already started to think about in terms of environmental change. Gas is input to the atmosphere, the effects of suddenly creating large topographic boundaries, and the effects then on redistribution of sediment as a result of these orographic effects. You can also get a situation where you have the collision of two plates, each of which comprises oceanic lithosphere, and of course the classic example of that is here in the Western Pacific. It rejoices in the name of the Isu-Bonin-Mariana Arc convergent boundary. And the reason I put that in, of course, is you have the Marianas Trench as one of the key elements of that, the deepest depression on the surface of the Earth. Now, interestingly enough, the oceanic lithosphere that's being subducted in this system is some of the world's oldest, but it's still relatively young if you look at your geological time scale. It's only up to about 180 million years or so old. This, of course, is one of the problems with getting older sedimentary records from oceanic basins, is that the oceanic lithosphere on which the sediments accumulate is effectively subducted and recycled. The final and classic example, of course, of a continental-continental convergence is the formation of the Himalayas with the northward drift of the Indian plate and its merging with the Eurasian plate, building the Tibetan Plateau that you see here, which is then flanked by the Himalayas, including Mount Everest, the average height of the Himalayan belt then being around 5 kilometers or so. And this is effectively the cross-section here, where the oceanic lithosphere has been subducted fully, and the two continental lithospheric plates, neither of them, of course, subducting below the other, and the two of them meeting with the inevitable formation of the mountain range along the suture between them. So just in general terms, we can start to think straight away of what moving these different sets of lithospheric plates across the surface of the Earth over geological time is going to do. So here we are. We start to alter things such as the ocean currents and circulation. We're going to have to redefine our models for how we redistribute heat over the surface of the Earth. If you've got more land at higher altitude, it's more likely. If all other variables stay the same, you're going to have greater likelihood of ice building up at high latitudes, because of course the ice is going to actually reduce the overall albedo of the Earth. If you change the proportion of the surface area in each climatic zone, you also potentially change the vegetation cover, the nature of the soil cover, for example. You'll impact on the albedo, and you'll also then, of course, impact on the thermal properties of the land and the sea as a result. So all of these variables operate both independently but also in an interconnected sense. Now, one of the key issues is the assembly then at certain times in Earth's history of supercontinents, when effectively the principal continental landmasses are assembled into one supercontinent. And the example I'm showing here is from around the start of the Triassic, about 200 million years or so ago. We start to break up a supercontinent that's known as Pangaea, and ultimately the product of that phase of plate tectonic activity is the distribution of the plates that we see today over the surface of the Earth. Now, the reason for putting this in at this point is you're going from 200 million years ago here to, there's Africa, moving a little bit to the east, South America a little bit to the left, or the west, of course, globally. And that's taken 200 million years or so to produce this configuration that we see today. So the rate of plate movement then is at best geological, quite literally, on the scale of centimeters every year. So the processes and the changes that redistributing the plates introduces in an environmental sense occur over these extended or geological time scales. But as we'll see, climate change can also occur on shorter time scales linked to plate tectonic processes as well. So let's just take a look at this point at this whole issue of the significance of supercontinents and their effect on climatic systems and environmental change in a little bit more detail, using the example of Pangaea. So around 225 or so million years ago, the plate tectonic system on Earth has assembled the major continental land masses into one supercontinent that's called Pangaea. From about 225 to 200, we start to see the initiation of the breakup of that supercontinent. and the key thing that we form initially are two major divisions, Laurasia in the north, and then to the south, Gondwanaland, and then over the subsequent geological periods, for example, the Jurassic through to the Cretaceous, ending around 65 million years ago, through to today, we start to see these splitting further apart until we reach the configuration that we see today. So we can reconstruct the environmental conditions we would expect with a supercontinent on this scale. One of the key things we see with the formation of these supercontinents is a phenomenon known as enhanced continentality. So, for example, while we will have strong monsoonal style circulation affecting coastal settings, the continental interiors are going to become extremely dry. Now, that's not necessarily synonymous with hot, of course, but effectively it's going to become very, very difficult to transfer moisture in any form of precipitation to these continental interiors. So they're going to become extremely arid. We're going to have extreme seasonal temperature swings between hot and cold. However, even though we're going to have extreme winter cold, it's going to be very difficult to actually sustain and build up any sort of persistent ice caps or ice sheets in mid-latitudes on any sort of continental scale. And the reason for that is not only because any ice that does form or any snow that does fall is essentially going to ablate or melt in the summer. Because of the aridity, it's going to be very difficult to transfer any precipitation to these continental interiors in the first place. Now, one of the key points about the disassembly of Pangaea and the emergence of the modern day distribution of continents that you see here is that this is in large part along with a decline in CO2 values in the atmosphere. This in large part is what is responsible for, from about the Paleogene on, the establishment of the Antarctica ice sheet.